Hey, this is my Introduction to Mathematical Proofs playlist. For our first proper video, we'll be talking about inequalities. Why inequalities? They're super nice to work with, come up surprisingly often, and provide a really good example of learning proofs. So, just be warned, I'll just kind of be tossing you into the deep end. We'll just jump right into it. No preparation, here we go. The thing is, when we think about math, okay, we want to prove things, okay? But we need something to start off of, right? So we need to have like a few basic rules that we can kind of use without proofs. These are called axioms, but these are things that we can take for granted. And here are the lists of things that we can take for granted when we're working with inequalities, at least at our level right now. The first thing is that every square number is greater than or equal to zero. Nice. That should make sense. Squares are positive. Just think of the graph y is equal to x squared. Nice. 2. If a is greater than b and b is greater than c, then a is greater than c. This should make sense. If 3 is greater than 2 and 2 is greater than 1, then clearly 3 is greater than 1. Then there's 3a, 3b, 3c. They're kind of similar, so that's why I kind of lumped them together, okay? So if a is greater than b and c is greater than 0, then when we multiply c to both sides, we'll still have that inequality. So c times a is greater than c times b. This should make sense if you're multiplying by 3 or 4 on both sides. If it was an equal sign, oh, it'd be the exact same. But now it's an inequality, it still stays the exact same. If 4 is greater than 3, then multiplying by 4, 16 is still greater than 12. Conversely, if it's a negative number, then what happens is the inequality sign flips, right? If you have 4 times 3, but then multiply by -1, we're going to get -4 is something to -3. Well, -4 is less than -3. And for 3c, same thing, we can just add the same number on both sides. So if 4 is greater than 3, if we add -4, or the same as subtracting 4, we'll have 0 is greater than -1. So that's why I kind of decided to clump them all together. And then 4 is a really weird one. This is when we're working with square roots, for example. If we have that a is greater than 0, we can find a unique number, well, a unique non-negative number. That's called the square root. So we call it the square root of a. And it pretty much acts like the square root. Square root of a squared is equal to a. That comes up for other things in the future. Okay. What we have is that these are kind of rules that we're used to, or rules that make sense. Everything that I said should make sense. Maybe number 4 is a little bit of an outlier, right? But we can also extend this a little bit more. So for 2 and 3, we can do two different things, right? So we can switch the inequality directions. So we replace every greater than sign with a less than sign and less than sign with a greater than sign. We'll still have the exact same things. If a is less than b and b is less than c, then a is less than c, right? That should make sense. And we can use non-strict inequalities. So before we were using these things called strict inequalities, like, okay, this is definitely less than, right? So a is definitely less than b. But then we can also have a is less than or equal to. We don't know. It could be equal, right? So we can use that as well. So if a is greater than equal to b and b is greater than equal to c, then a is greater than equal to c. Pretty much we're given rules to manipulate inequalities. So what can we do? Okay. So we can do what we call cancellation. So we just have one inequality. If a plus b is greater than c, that's the same as a is greater than c minus b. Okay, well, how do we show this? Well, let's just start with a plus b is greater than c. Then we can add in negative b to both sides. This is by 3c. 3c allows us to add the same thing to both sides and still maintain the inequality. And we added negative b, so it's the same as doing minus b. And then b minus b is equal to 0, so we have a is greater than c minus b. We know that b minus b is equal to 0. Wait, is that even true? What is negative b? Does negative b even exist? Like, how does that work, right? Is it always true that a plus b is equal to b plus a, for example? You know what I mean? So there's so many ways that we can think about it, and that formalization exists, right? And we'll actually talk about this later down the line. But we'll continue talking about inequalities. Now, just one final note we do. Since this is the first proof we did, we start off by saying that, oh, hey, look, this is the proof. We're telling our reader, hey, this is a proof that we are starting. Then we explain what's happening. Then we put a little square at the end, or maybe a QED, and this tells us, hey, we have completed the proof, so your reader should know that we're done. So let's actually solve another problem, right? So if 0 is less than a, which is less than b, so this means that a and b are both positive, then we want to show that a squared is greater than b squared. Okay. I just have the proof here. We're just going to run through it very slowly. So we start off with a is less than b. Then what we do is we're going to multiply b on both sides. So we get a times b is less than b times b. but that's the same as b squared, so a times b is less than b squared. But now, since a is less than b, we have that a times a is less than a times b, right? And a times a is just a squared. So maybe this will make sense. If a is less than b, you can also multiply by a on both sides, or just notice that a times a is less than a times b. There's a few ways to see that, but make sure that each line makes sense. Then we can actually combine these together, these two lines, right? We get that a squared is less than a times b is less than b squared, because we're chaining the thing on both sides, right? Then by rule 2, we can combine that together and see that a squared is less than b squared. So what's really, really important when we're doing proofs is making sure we understand every single step. Remember, that's one of our main goals. Make sure we understand the proofs that are happening, right? So of course, this is something that should be true, okay? If a is less than b and both of them are positive numbers, then a squared is less than b squared. But we need to prove it, right? And that's why we use the rules that we already have to prove these types of things. And once again, make sure that every single line makes sense. Okay, now just a quick little exercise. We have the same starting condition. 0 is less than a, and that's less than b. Now, how would you show that the square root of a is less than the square root of b? Hint, because we're using square roots, you might find that using rule 4, the thing about the square root, might be really, really useful. So now we're going to be talking about the triangle inequality. This is a pretty important inequality. What is it, you might be asking? Let's first provide a visual. So the idea is this. We're going to draw a triangle. Let's label them A, B, and C. Sure, that's fine. What we're going to do is we're going to talk about the relationship from one side to another side, right? So we'll notice that if we pick any side, that one side is larger than adding up the other two sides, or adding up the length of the other two sides, right? So in this case, going from A to B is shorter than going from A to C than from C to B in terms of length. Okay, so we see that the blue line is definitely shorter than the other two lines because it's definitely shorter than the middle line, right? But what if instead we choose the middle line? Will we still have the exact same thing? And clearly, if you just rearrange it a little bit, yes, it just seems to add up. Don't mind the little gap. That's clearly overlooked by the fact that adding up the two red lines is larger than the singular blue line. So how do we actually algebraically display this fact, right? How do we express what it means for a side length, okay? In our case, we're going to be working and looking at the one-dimensional case. It is a little simpler to understand and prove, and the math behind it is also not as hard. So let's start. On the number line, we're just going to write A, B, and C, right? And after drawing these lengths, we can see that the line from A to C is the same as going from A to B, then going from B to C. So as long as line is indeed equal to adding up the other two lines. Don't worry, the little gap is just so you can differentiate the lines, but in actuality, when you add them up, they'll be the exact same length. And if we did instead choose A to B, well, A to B is definitely less than adding up the other two lines. So now the question is, how do we get the length or the distance from any 2 points? Well, we just subtract 1 point from another. If you don't believe me, just play around. Of course, the idea here is it's not just, oh, what I say is true. No, what I say is intuition, and you should verify that intuition. Or what I say might be true, but you don't believe me. So play around with it and believe me, right? Don't just trust me blindly. Think about, okay, why is that true? Does that make sense to me? So what we'll kind of figure out is, let's look at the difference between A and B, for example. If we do 2 minus -4, we get 6. And that's indeed the difference between A and B. That's the size difference between A and B. But if we did -4 minus 2, we get -6. So we get like a negative sign. This is kind of annoying to work with. So what we're going to do is we're going to introduce an absolute value. What an absolute value does, if the number is positive, we just don't touch it. If it's a negative, we'll flip the signs. So we'll just put that definition in the bottom right here. And we'll introduce it later because we're actually going to work with it. So now we have 3 distances that we're working with: A minus B, B minus C, and A minus C. So we get our most primitive version of the triangle inequality. A minus C is less than or equal to the absolute values here, A minus B plus the absolute value of B minus C. But wait, A minus B is literally just a number, and B plus C is literally just a number, right? So what we do instead is a little weird. We're going to represent A minus B with the absolute value of a minus b with a single number. We call that the absolute value of x, and b minus c with absolute value of y. Then our new inequality is going to be the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Now, a question you might have here is, why is the absolute value of x plus y just appearing out of nowhere? Well, we want to show that the distance between a and c is less than or equal than the distance between a and b added with the distance between b and c. So pretty much we want to prove that x plus y, an absolute value of that, is indeed the shortest distance between a and c, or if not equal to the shortest distance. So this inequality is actually literally what we want to prove. Maybe you don't believe me. Well, of course you don't have to, right? Just play around with it. Because for me, what I do is, okay, let me just play around with this fact in my head. When I first saw this, I'm like, okay, let me play around with different values of x and different values of y. Remember, the absolute value just makes things, if it's positive, keeps it positive, if it's negative, keeps it negative. So try a different values of x and y and see what happens. Maybe 2 and 6, make them negative, positive, and play around and see what happens. But we need some rules on how to handle these absolute values. Because if we don't know how to use absolute values, how are we going to handle the inequality, right? So the first is that a is less than or equal to the absolute value of a. 2 is absolute value of a squared is equal to a squared. 3, the square root of a squared is the absolute value of a. And 4, the absolute value of a times b is actually the same as the absolute value of a times absolute value of b. If none of these make sense, then just think about why these would be true, right? For 1, a is either positive or negative, so clearly that makes sense. For 2, when we square absolute value is the same as squaring the number itself. For 3, square rooting it always gives you the positive value. If you have negative 3 times negative 3, that's 9. The square root of 9, there are technically 2. For this example, we're going to go with a positive one. So that's why we go with the absolute value sign. And for 4, well, no matter which ways we multiply it, inside if we multiply it, on the left side it'll be a times b. If that's a negative, well, it just becomes a positive. And then the absolute value of a is positive times the absolute value of b, which is positive, is still positive. We want to show that the triangle inequality holds, right? And this is actually going to be a little tough, but the question is, how do we start? What do we want to do, right? So ideally, we want to prove this. So that means we want to go from something true, something that's like fact, to the inequality itself, right? But then the idea is, where should we start? If you pick randomly, okay, I'm gonna start with this thing and then go there, it's not really gonna work. But what if we go backwards from what we want to prove and see if we can get some hints, right? The idea is, if we go backwards using logical steps, then we should be able to construct our proof backwards. That makes sense? If we have A, then B, then C, then D, and D is what we want to prove and A is something that's true, well, in order to find A, we might do D. Well, what can we do after we get D? Maybe go to C, then B, then A, and then, oh, hey, look, we reached something that's true. And since the steps between are logical and sound, we should be able to go back when we're proving it in the reverse direction, starting from A, what is true, to D, what we want to prove. Let's play around with what we have right here, okay? So on our first line, we have x plus y, all absolute value, is less than or equal to absolute value of x plus the absolute value of y. So what could we do? Well, I'm thinking let's just square both sides and see what happens. Why would we want to do that? Well, a lot of the rules that we have work really nicely with square values, so maybe we can manipulate some of what we have to get to something true. So we square both sides, and then, hey, it looks like we can expand the right side, because we just treat absolute value of x and absolute value of y as just a number. And then we'll get absolute value of x plus y squared is less than or equal to absolute value of x squared plus 2 absolute value of x, absolute value of y, plus absolute value of y squared. It's a lot to say. Okay, nice. And let's use the rules where we turn anything absolute valued squared equal to anything squared. And then what we'll see is that this gets rid of 3 absolute values in our equation. And wait, now we can expand the left-hand side. So, okay, let's expand that left-hand side out. And then, wait, we can get rid of the x squared and the y squared. And then at the end, we just have 2xy is less than or equal to 2 times the absolute value of x times the absolute value of y. So we'll divide by 2 and use rule 4 to get x and y together, and bam. xy is less than or equal to the absolute value of xy. Now we're at something true. This is something that we know is true. This is rule number 1, with just xy instead of whatever value we want. So now we'll just repeat the step backwards and just construct our proof. So I'll just write it up on the slides what the complete version looks like. I won't go through it properly, right? So we did the proofs. So we take rules that are true and use them to devise other rules that are either that are more complicated or things that should make sense to us. And we can keep going about this process, right? And one thing that's interesting is, at least right now, everything that we did just requires some simple arithmetic or algebraic identity, right? But then the question always becomes, how would I come up with this myself? For example, if I told you to do the question on first, which I will from now on, then the question is, okay, sure, I can follow along with how you do it, but then how would I do it myself? And that's always the question. That's always tough. That's always how it is, right? And part of that is getting the exposure and just working on things together, right? And honestly, you just have to play around and see what happens, right? That's all we can do, right? So for the triangle inequality, how am I supposed to know that I'm supposed to square both sides? Just play around and learn, see what we can do, right? Think of all the rules that we have, right? Just in this case, we had a lot with square values, so that's why it was really nice to work with. So once again, we just want to, at the beginning of the course, we just want to introduce you to the idea of proofs, right? So this is the idea of proofs. We're using things that should be similar to what you know, so inequalities, right? Next video, we'll be working with even and odd numbers and primes and composites and easing in other proofs that way, right? But that should be it for this time. So I'll see you in the next one.